Okay, you're given this function right here, f of x equals x cubed minus 6x squared plus 9x minus 4, and asked to find the local or relative maximum and minimums using first and second derivative tests. Okay, so here, this blue graph is the graph of f of x. This light green dashed line is actually the graph of the first derivative. And this red line is a tangent line at the point where, well, I don't know what the x coordinate of that point is. But here's two observations. For a given function, its first derivative is actually a formula for slopes of tangent lines to the graph of that function. And when the first derivative equals 0, the tangent lines at that point are horizontal. So here's this red tangent line moved up to the point where x equals 1, where the first derivative is equal to 0. And you can see that the tangent line is horizontal. And at the point where x equals 3, which is the other point where the first derivative equals 0, the tangent line is horizontal. Okay, so the question is, how do you use the first and second derivative tests to identify 1, 0 as a relative or a local maximum and 3, -4 as a relative minimum? So here's how it happens. Here's the original f of x. Here's f prime of x using the power rule. 3x squared minus 12x plus 9. Here's the second derivative, 6x minus 12. First, we want to find the critical numbers, which occur when the first derivative is equal to 0. For some functions, it's also true that there are critical numbers when the first derivative is undefined, but for polynomial functions, we don't have to worry about that. So to find the critical numbers, set the first derivative equal to 0. I won't go through the steps, but there's your critical numbers. And so this little diagram here shows the first derivative test. We put the critical numbers 1 and 3 on a little number line. And then we talk about what f prime of x means for f of x in numbers on either side of those critical numbers. So for example, pick a test number to the left of 1. I picked 0. F prime of 0 is 9, which is positive. And when the first derivative is positive, the tangent lines are going uphill, positive slope, which means the original function is increasing. If you pick a number in the interval between 1 and 3, like 2, f prime of 2 is negative, which means the tangent lines are going downhill, which means the original function is decreasing. And similarly to the right of 3, tangent lines are positive, sloping uphill, so the original function is increasing. This little diagram tells you that at 1, there's a relative maximum because the function is going from increasing to decreasing. So there's a relative max at 1. If you want to find out the y value at that critical number, you find f of 1. You put 1 in for x, and you find f of 1. Since the original function went from decreasing to increasing, there's a relative minimum at x equals 3. And you can go back to board 1 to see that. To the left of 0, the original function is increasing. To the left of 1, to the right of 1, the function starts decreasing, and then at 3 it goes back to increasing. Okay, now right here I've got a test for concavity, which uses the second derivative. Whoa, that isn't really necessary to apply the second derivative test, but it helps to explain why the second derivative test works. So when you set the second derivative equal to 0, you find out that x equals 2. In the old days, we used to call this a hypercritical number. I don't think textbooks do that anymore. But if you apply the same idea, put little 2 on the number line, the sign of f double prime to the left of 2 is negative. I tried f double prime of 0, got negative. And when the Second derivative is negative. That means the tangent lines are decreasing in slope, so the original function is concave downward. And I like to think of that as a frown. Negative equals frown. To the right of 2, the second derivative is positive. So the tangent lines are increasing in slope. Picture this, increasing in slope. So the original function is concave up. Think smiley face. Positive equals smiley face. Oh, so we say that there's a point of inflection at x equals 2 where the concavity changes. Now, how does that apply to the second derivative test? Because if you plug these critical numbers, 3 and 1, into the second derivative, you're actually finding out whether at that point the original function is concave up or concave down. So f double prime of 1 is in this interval right here to the left of 2. And we know to the left of 2, the original function is concave downward. And since the slope at 1 is 0 and the curve is concave downward, there's a maximum. So when the second derivative, when the value of the second derivative is negative at a critical number, then you've got what's called a relative or local maximum. And f double prime of 3, which is to the right of 2, is positive. We know that it's concave up, smiley face. Slope is 0 at that point. So there's a relative minimum at 3. Max at 1, min at 3. Okay. And when I post the answer to this, I'm going to also post a link to this Desmos graph. You can play around with this point, which is a slider for the tangent lines. And it also has a line for the second derivative. You can see where that the second derivative is 0 at x equals 2. Okay, there you go. Hope that helped. If you have a question, post a comment.